through another account I will be monitoring, uh, so that if you have any doubts, you put it in a chat box when and then I'll take up at the end of the session. So once again, good morning to all. In the last class, we were discussed about a few of the important, very fundamental concepts of digital signal processing, and we've gone through the content that is present in your first chapter, and we have discussed about what is the digital signal processing and why digitalization is required, and we went through this particular block diagram. We could able to understand the importance of digital signal processor, and this is how the block diagram looks. Block diagram of DSP looks, and most of the time this particular DSP is going to be used to uh, just we will be using this particular digital signal processor for processing digital signals. So if at all here onwards, you should remember that the type of signals that we are referring here, it is all the time x of n signal. The reason is, so x of t signal will be a continuous with respect to time, and x of n signal is a one signal which is going to be a discrete time signals. So here we are least bothered about the x of t signals, as it is a analogous and continuous signals. So we almost all the times we will be taking up the discrete time signals, which means even if there is a input signal is analog signal, so later in point of time we convert that into a digital signals by making use of analog to digital converter. Then these signals are sent to digital signal processor, and you perform some mathematical operations, and then once again the output will be in the discrete form itself. So this discrete signal again will be converted into analog form, and then that will be our the final version of the signals. Then followed by, this is how the importance of the digitalization, as we told that. So if at all I have a voice signal or audio signal in my mobile phone, then later at point of time I want to transfer that data to some xyz person, then from the memory, the DSP signal, the DSP processor fetches that particular signal. So all this data it considered to be as a signal processor processing all the data. Either you store it in MP3 format or MP4 format. Everything is a data, and that data is nothing but a signals. So that signal has to be fetched by the processor. Hence, we will be using a dedicated DSP chip inside your mobile phones, and from the memory, the processor fetches the data, and then that data will be stored in digital format. Then later in point of time, it converted into analog, and then when we actually user see that, they don't feel any difference, because input is also in the form of analog and output is also in the form of analog, but entire thing that is going to be processed within this, it is by the DSP processor. So this is what we discussed, like why analog systems are not preferred, and what's the advantage of digitalization over the analog components. Now coming to the types of signals, in the third semester itself, in the signals and systems, you have studied different types of signals. So mainly continuous signal and discrete time signals, and other way random signals, and the next type of signal is somewhere else, odd signals and even signals, right? And the very important is periodic and non-periodic signals. Periodic and non-periodic signal. What do you mean by periodic signal and non-periodic signal? Okay, can put it in chat box. I'll be watching your answers in my another mobile phone, so that I can able to view your chat box answers. What do you mean by periodic signal? What do you mean by periodic signal? Yes. Periodic is one which varies with the time. Okay, very good. Any other answers? What about aperiodic signal? Anjana Naik says that which repeats after regular interval of time, and Nivedita say measurable in time frame. Okay, Devidas answers in it. It is, if it is repetitive, it is periodic. Very good. If it is repetitive, then it is periodic. Can you give example, Devidas Naik, for repetitive signal? Sine wave, uh, in cos wave. Okay, you mean to say that sine wave will going to repeat after every some time. Okay, let me take up this very simple concept here. As Devidas Naik and I think Agna Naik rightly pointed out, which repeats after regular interval of time or it is repetitive. So such signals are called as periodic signals. So, okay, a very simple example I will be taking. So that is what I cannot take the example that what Devidas Naik told about, which is sine wave and cos wave, because every signal in this world can be represented as a sinusoidal form or a cosine wave form. I take a sine, I can represent sine in terms of cos, or even cos can be represented in terms of sine. Is it not? So every time, even a tidal, the tidals of sea is also represented as in the form of mathematical representation. If I go for representing those signals, again I represented those signals are going to be represented in the form of sinusoidal waveform itself. And you consider the speech signal, even that particular signal is also represented in the form of sinusoidal signal itself. In the entire globe, if any signal is there, we try to develop that signal to represent it with a trigonometric function, and that trigonometric function is sinusoidal waveform. Okay, sinusoid. Now let us come to this particular point. The periodic signal is one which going to be repeat after some times. Once again, this is first cycle. Okay, this is first cycle. Again after some time. So this is in with respect to time I am speaking. Okay, and again after some time the same signal going to be repeated. What does it mean? I'm slightly due to my I'm not able to give it a convenient way, but I'll say you this is frequency f1, and the next signal is also having a frequency of f1, not f2. If it is 50 hertz, the first cycle is of 50 hertz from 0 to 2 pi, the next 0 to 2 pi is also 50 hertz itself. I think someone is waiting. Let me admit them. Okay. Students who are joining at 9:15. This is not the timings, guys. I don't want to come back and give the admit option every time. So I request all the guys from the next class to come 5 minutes before. Thank you. I'll go back to the session now. Okay. Okay. Now the real-time example where this signal, where this signal are going to be same is, take a real-time example of 220 volts 50 hertz signal. What is this? What is this signal is all about? So this signal is the voltage that is going to be spread across all the homes in our country, the signal is the voltage is around 220 volts and its frequency is 50 hertz. Normally you will be knowing and you are thorough with this, right? So is it a periodic or aperiodic signal? It must be a periodic, right? So the AC signal, which must be a periodic, the reason is all 24 cross 7 and 365 days. As time changes, the frequency of that signal is unaltered. Hence, this is one of the best example to say that the periodic signal. What about a periodic signal? What about a periodic signal? Which is the example for a periodic signal? A periodic signal means the signal which are those signal where you don't have a constant frequency as the time changes. The frequency of a signal varies as the time varies. The best example for a periodic signal is your heart pulse. Now when you right now you are sitting calm and quiet, the pulse rate of your heart is around per minute 72 or 7 in between 70 and 72 or 75. But when you made through a walk or when you make through the run on a treadmill, or if I ask you to run for 100 meters or 200 meters, if I keep a competition, then definitely your heart pulse will varies, right? So that's what I told you. As the time changes, the frequency of the signal will be never constant, and such a signal we call them as a aperiodic signal. Similarly, now I'm speaking to you guys. My voice signal is also one of the best aperiodic signal, because the whenever I talk to you, there will be a voice modulation, and because of the voice modulation, the frequency of my signal of my voice signal is going to be varied. That's how if I recorded, when you see the recorded audio or the recorded video signals, and if you observe those signals in TV or even in your mobile phones, you just play a recorded signal, you can see this kind of signals, right? So what does it mean? These are nothing but my voice signal. I am trying to represent it in the form of sinusoidal waveform, which comprises of different frequencies. If I talk f1 frequency for 1 second, in the very next second my frequency will be f2. In the another half an hour, after half an hour, my frequency may be f3. It is not constant. It is not, I cannot say that the frequency is 20 hertz or frequency of my voice signal is 40 hertz, or it is so on. It may vary as a time vary. This is the best example. Heart pulse and your voice signal and speech signal, all these are the best example for a periodic signal. Now coming to the point, where uh, now, whenever we have a signal like these kinds of whenever we have these types of signals, so I want to analyze a periodic signal, which means that all the time especially in case of signals and systems or in a digital signal processing, we always want to go for frequency analysis. We why we should go for frequency analysis, that I will going to take it in a separate class, the reason why we go for frequency analysis. But all the time, make sure that if there is a signal in a time domain, we always shift into frequency domain. We analyze the particular any signal is going to be analyzed in frequency domain. Then later in point of time, once again we come back to time domain, and then uh, we propagate this particular signal in the real time. But whenever we want to perform any signal to be a frequency analyzed, which means that I need to convert this time domain signal into frequency domain signals. So I'll just erase these signals like. Okay. Now, whenever I want to analyze the signal, maybe x of t or it may be x of n. So, periodic signal will also consisting of a CT signal, and periodic signal may be discrete time signal. Similarly, the aperiodic signal also may be the continuous time signal, or it may be a discrete time signal also. So now, whenever I want to analyze movement from time domain to frequency domain, so I want to analyze this signal in the frequency domain. If this signal x of t or x of n is periodic, then simply apply Fs, that is Fourier series. If the signal is a periodic signal, that is maybe a continuous time signal or it may be a discrete time signal, whenever I want to analyze this particular frequency in this particular signal in frequency domain, then simply apply Fourier transform. So unless you differentiate the signal, whether the input signal is periodic or whether the input signal is aperiodic, you cannot you cannot go for whether you cannot say whether you are trying to apply a Fourier series or Fourier transform. Randomly, you cannot say I will apply a Fourier transform or I will be applying a Fourier series unless you know whether the input signal is whether the input signal is periodic or aperiodic, right? So that's where now why we are going to digital signal processing, and why we are concentrating more on DFT. So probably you will get to know now, in this instant itself. See, as I told you, digital signal processor will going to where do you find these? Most of all in mobile phones and in your ECG machines and in CT scan machines, all those machines. And if you observe those signals, are they periodic signals or are they non-periodic signals? In all these cases, take your voice signal, take your audio signal, take your any video signal, will they remain same with respect to frequency, or will those signal vary as with respect to time? So definitely they will be varying with respect to time. Hence, I will be applying a Fourier transform for aperiodic signals. Is it not? So if a signal is periodic, I will be applying a Fourier series, and if it is continuous time, I will be applying a continuous time Fourier series. If it is a discrete signal, I will be applying a discrete time Fourier series. If again in case of Fourier transform, the Fourier transform is applied all the time for the non-periodic or aperiodic signal. If the signal is CT signal, then we will be going for continuous time Fourier transform. If it is DT signal, then we will be going discrete time Fourier transform. I hope this particular the chart is very clear to all. Shall I proceed for the next slide here, guys, or you have any doubts? Any doubts here? Okay, I think if there is no response, like I will be moving for the next slide here. Okay, 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 good. Thank you. Now, the one more question here. Now, if uh, if I go for the digital signal processing, I will be always saying that the signal is discrete time signal. So hence our discussion will never be with respect to this part of the point. So I will be always concentrating, or entire DSP will be concentrating on these types of signals now. So where my signal, I assume that whenever I give a x of n value, you simply think that it is a periodic signal, and once there is a periodic signal, I will be going for a FT signal, Fourier transformation to apply here, and then if it is CT, we will be going for CTFT, and there is no point of discussing this CTFT signal, because we are processing digital signals. When I say that digital signals, you must assume that it is a x of n. This thing you should have in your mind. Fix this x of n in your mind throughout the DSP subject. So now once there is a x of n signal, then it is only you need to apply a DTFT for that. Right? So now all the things are very clear. So since I am not applying a Fourier series here, because we are not discussing the periodic signals. In the entire DSP, we will be discussing about periodic signals. So now once we are going for periodic signals, since the processor is processing only digital signal processing, and we are worried about analyzing discrete signals. Hence, I will be concentrating on this portion only. So now our next intention is to go for DTFT signals. Okay, so if at all there is a signal, to perform a frequency analysis of a discrete time signal, they are to be converted into an equivalent frequency domain in the frequency representation. Now what is this all about? So if this x of n is considering as a DT signal, and this x of n is a periodic signal. So therefore, what I should do? I must apply DTFT in order to obtain its equivalent frequency domain. Right? So since the frequency analysis of discrete time signals, that is x of n, are usually carried out because we are processing a digital signal process. We are using digital signal processors. That's a very important point here. Now, coming to this particular part, the Fourier transform of discrete time periodic signals. Read out the sentence. The Fourier transform of discrete time periodic signal x of n is continuous of omega and is periodic with period 2 pi. What did you understand? What did you understood from this? So that is, let me take once again a very good example here. Let me consider x of n signal is there, and this x of n I am trying to, what is this x of n? This is a discrete time signal, followed by this is a periodic signal. Now when you have these kind of signal, when I go for frequency domain, usually it is x of omega, or sometimes we also represented this as x of e to the power of j omega. Both are correct, guys. Both the representation are perfectly okay. Now this is here, it was varying with respect to samples. X of n was varying with respect to samples. This was the x of n signal. Now this particular signal is varying with respect to frequency, that is omega, and this particular frequency omega, the x of omega, after applying DTFT, a discrete time aperiodic signal will be converted into what type of signal? This will be continuum frequencies, and that will be periodic with respect to 2 pi. So that is what the meaning. So the output of DTFT x of omega. So this is a DTFT signal. When you apply DTFT mathematical computation on input x of n, which is discrete time and aperiodic, when you apply a mathematical tool, discrete time Fourier transform, the output of DTFT is always continuous, first point, and second one, it will be converted that particular signal into periodic signal. This is very important, guys. Unless you don't know this, so we cannot go for DFT. Okay, all these things, DTFT, CTFT, and entire thing you learnt it as a one separate chapter in our signals and systems. So that's why I'm not getting into deeper and deeper here. I just brushing your basics, that's it. So you already learned how the equation, so how this particular equation make a change or make this impact on x of n, so that my output signal x of omega will be a continuous and periodic. Okay, so one thing what you should remember here, if x of n signal is a aperiodic and discrete time, its DTFT is a continuous and periodic. So that is what the x of n signal, the Fourier transform of discrete time aperiodic signal, which is x of n, is continuous function of omega and is periodic with time period 2 pi. So after every 2 pi, the signal will going to be repeated. So this is one of the fundamental important concept. So now in the next slide we will go with relationship between DTFT and DFT. Okay, so we'll try to understand the detailed equations and understanding with respect to DTFT signal, and how the relationship between, so this frequency domain sampling and reconstruction of a signal is mainly on relationship between DTFT and DFT, which will be periodic with period 2 pi. Now, before going with this, I'll just have a small analogy why we consider that periodic signal to be period, and why we go for sampling in frequency domain. So now, as I told you, the DTFT signal, it is what type of signal? It is DTFT is a, you applied discrete time Fourier transform, but the output is not discrete. X of omega is not discrete, it is continuous signal, and this is periodic with respect to time period 2. Now the question is, how come there are no discrete signals at all? How come you can able to obtain the magnitude of this, I'm sorry, the phase of this and magnitude of this? It is very difficult to obtain the magnitude and the phase, one thing. Second thing, in the DSP processor, if I want to process, what type of signals are required here? Discretized signals are required. Now I applied Fourier transform, but this Fourier transform is continuous signal. I don't have any discrete signals. Now, if I want to get the discrete version of this, what operation I should perform on x of omega? Can anyone put it in chat box? What operation I should perform so that I am going to get the discrete version of x of omega? What operation I should do? What operation, guys? I'll give you 1 second. You can think and let me know how I can able to fetch the discrete values of DTFT. What operation I should perform? Guys, are you there or not? Chaitra Kulkarni? Are you there? Amruta? Abhay Bhatt? Say yes or no. Are you connected to me? DTFT signal is a continuous signal. Now the DTFT signal is continuous. So this is x of omega, and assume this is nothing but a DTFT signal which is a function of omega. Now this is not possible to process in my DSP, digital signal processor, because it is again a continuum of frequencies. Now what procedure I should follow in order to get discrete value into my system? I need to get this kind of discretization signal, right? How do you get this type of signal? What is the solution? Now it is very tough. The reason why we don't prefer DTFT is you cannot calculate the phase and magnitude of this. This is very difficult to obtain the phase and magnitude of DTFT signal. And again, if I want to process in the digital signal processing, this is not a discretization signal. This is once again a continuous signal. Continuous signal I cannot able to store or I cannot able to process in the processors, because always processor requires digital signal. Then what is the solution? How do you obtain this kind of signals? How do you obtain this? From this, I need to get this kind of signal in the form of x of n or discrete signals. What is the solution, guys? This kind of signal. What is the solution? How do you obtain? This is now, right now you have continuous time signals. What do you do? Put it in chat box. Am I audible? What is the solution? I want to fetch this. Yes, assume that you have one cake piece of a complete cake, which is a circle form. Now you want to share this for amongst your four of your friends. What you do? What you do? You want to share this cake amongst your four of your friends. What you perform? What process you follow? One student I give the answer. I sampling. Any other answers? Let me take this example and then differentiate. Okay. Any other answers? So this cake is going to be cutted equally into four parts, right? So that I am going to get a piece one, second piece, third piece, and fourth piece. Okay. Now, is it not a kind of dividing this entire circle? Which is nothing but when I say that I am trying to get a piece of sample from this cake, right? So assume that if I want to share this, or if I want to divide this, minimum how many pieces can be divided? I am asking about minimum, not maximum. Minimum ಅಂದ್ರೆ ಎಷ್ಟು piece ಆಗುತ್ತೆ? If I cut this entire cake. Very good. That is what we call about. That is what we call about the sampling rate of the frequency must be greater than or at least equal to two times of your actual frequency. The sampling frequency must be two times this, right? So if I want to sample this, and at least I want to have a sampling rate. That is what you have learned it in your communication subject. So if I want to sample a simple signal, at least I need two times that particular frequency, right? So similarly, here also I want to go for discretization. I want to go for discretization. What I do? I collect the samples, right? So I'll just I collect this, I go for sampling this signal, right? So I go for sampling this signal. Since the signal is the DTFT signal is moving from minus infinity to plus infinity, but as I told you, this signal is periodic in nature with period of 2 pi. I consider only first cycle for the analysis purpose. So minus pi to plus pi assume. So which means that for every, why do we say that periodic? For every after 2 pi, the cycle is going to be repeat from 2 pi, from 3 pi to 4 pi. As such, the cycles are going to be repeated. So in such cases, so the next cycle, if I consider this cycle is once again, this sample is once again as same as this first cycle. So I consider this as a first cycle. Okay, I consider this to be a second cycle. The first cycle and second cycle will remain same because they are periodic, because the frequency is unaltered, right? Even if I consider today is also frequency of 50 hertz, I will be getting at my home. Tomorrow if I measure the frequency of the signal to 20 volts, again I will be getting a 50 hertz. So it is necessary and sufficient if I analyze one cycle, is it not? So what we do, it is as good as a cake piece. It is as good as a cake piece. I'll be cutting equal pieces. Now it is a periodic signal. I take one of the piece and then I'll measure its width. I will measure its height. That is sufficient for me. So that is what the analysis I do with respect to a piece of cake, so that all the rest of the pieces are same. Is it not? Similarly, here also I go for one complete cycle which is of period from 0 to 2 pi. Why we consider to 0 to 2 pi? Within short time I will tell you why only 2 pi we consider it as to be one cycle. Audio is not clear? Now is it okay? I'm a bit loud and I'm very near to laptop. Is it okay? Okay. No. This is where I try to sample the each one of the signal, right? So now you know that what is the DTFT equation? X of omega is equal to summation minus infinity to plus infinity, n is equal to x of n into e to the power of minus j omega n. So this is my DTFT equation, right? Now in the previous slide, look at this. I cut a single piece. Now I take this apart. So I'll take this apart. Here in this cycle, I write it only one cycle, right? So I consider to be only one cycle here, because I may go for considering from minus infinity to plus infinity. Since the cycle is periodic, it is necessary and sufficient to consider only single cycle. So now what I do, I go for sampling of each cycle, each signal. So if I consider this to be 0 to 2 pi as a one cycle, now let me consider the signal is 0 to 2 pi, and if I go for sampling like this for n number of samples, for n number of samples. So what is the distance of each sample from this to this? What is the distance of this? So this is nothing but omega. What is delta omega here? The entire omega is 2 pi range. What will be the sample of this signal for one sample? So entire signal we are considering for one cycle, and we are sampling this for n number of samples. The distance between first sample to the second sample will be 2 pi by n. Is it not? Is this clear? Guys, why 2 pi by n? So now of such, how many samples I am going to get? See here, this I consider this to be for only one cycle, but my signal is ranging from minus infinity to plus infinity. I can take this 2 pi by n in one of the cycle. Again in the second cycle I can consider one more 2 pi by n, and this continues. So initially I call this for the first cycle. So here I repeat this once again. So x of omega. So x of omega is running from minus infinity to plus infinity. Minus infinity to plus infinity. Upon this I consider only single cycle. In this single cycle I am sampling samples from 0 to 2 pi, and each sample size is of 2 pi by n, because there are n number of samples in one cycle. Of such how many cycles are there? So one, this is I represent this k equal to 0th sample, and next will be a k equal to first sample, and this continues k equals to up to n cycles, right? Of such there are n cycles, so therefore 2 pi by n of such ಇಂಥದ್ದು ಎಷ್ಟು ಸ್ಯಾಂಪಲ್ ಕಲೆಕ್ಟ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ, ಮೈನಸ್ ಇನ್ಫಿನಿಟಿ ಇಂದ ಪ್ಲಸ್ ಇನ್ಫಿನಿಟಿ ವರೆಗೂ k number of samples I will be collecting, right? So what happens now? X of e power j omega, x of omega badlu, so omega is sampled from each sample having 2 pi by k, that is equal to summation. Now n will be running from 0 to n minus 1 samples, x of n e to the power of minus j. In place of omega, what is the sampling rate? 2 pi by n kn. So now I replace this omega with 2 pi by n k, that is equal to summation. I consider instead of 0 to, see, the reason is since it is periodic, I go for n number of samples. N number of samples means if I consider from 0, it is 0 to n minus 1, and x of n e to the power of minus j omega badlu, in case instead of omega I will be considering 2 pi by n kn. So since 2 pi by n, 2 pi is constant, n will be also constant based upon the number of samples that you take. So it is x of k is equal to summation n equal to 0 to n minus 1 x of n into e to the power of minus j 2 pi by n kn. So this is my DTFT equation. So this is the equation for sorry, not DTFT, this is the equation for DFT. So here I had, here it is DTFT equation. From the DTFT equation we derived the DFT equation. So now look at this, DTFT was continuous time and periodic. What about x of k DFT? What about x of k DFT? Please let me know what will be x of k, whether it is continuous or it becomes discrete now. We took a sampled version and there is a summation. What it should be? Guys, quick. Are you there? Are you there? Discrete. Is it must be discrete and very good. So now the DFT is hence it is called as hence the name discrete Fourier transform. Discrete Fourier transform. So I hope this session was clear to each one of you. And here we will stop for the day. And in the next class, I'm going to take up the few of the problems on DFT. And anyways, the recorded sessions will be put in Google Class later point of time. If you have any doubts, please go through the